Okay, welcome to Lecture 10. I'll begin with a Jupyter notebook where I'm going to give you another example of LSTM. Last time I left off with this implementation of RNN, where I define my own data in the form of text string, and then I tried to train my RNN LSTM basically based on that. And today I'm going to go for some standard data which is available. So like always, after including the necessary libraries, I'm going to go and look into this data. I'm going to use this Jena climate data. So this is data with 14 different quantities. They were measured over a span of time from January 1st, 2009 to December 31st, 2016. So a large number of data values are available. The values that they gathered, it's about weather or climate data. So air temperature, atmospheric pressure, humidity, wind direction, all that kind of parameters were there. And they were recorded after every 10 minutes. So it's a large data set. Okay, so I'm going to upload it. It's available in TensorFlow as its Keras databases. So I've uploaded the CVS file, which is in the form of a zip file. Once I load it, I'm going to load it in the file. I'm naming it like this. Okay. Once I've got this file in it's in zipped form, I need to unzip it. So for that, I'm going to use the OS path split text to give me the CVS file. So CVS file now I can read in a Panda data frame. So to make a data frame, I call Panda read CVS. So a data frame is formed now. So a data frame is nothing but a table, like an Excel table. Okay. And you've got you can see the head and tail or the complete data frame. So as you can see, you've got the index here, you've got time and date. You can see the time, especially the date, is the same time is going in 10 minutes. And you've got pressure, temperature, etc., etc. Everything is there. So it's data with 420,000 rows and 15 columns. Okay, I'm not going to use all of that. I'm going to pick one column of this data, like temperature. Okay, so it's a temperature in a city, and we want to see how the temperature variations are going on. What I'm going to do is this: I'm going to split this data in 3 parts: training part, validation, and test. Okay, and I'm going to train my LSTM for the training part, and then along with validation. Okay, so the training can be done along with validation. So it will do the cross-checking while it is training. It will try to optimize. Once it is done, then I'll check how good the trained network is for the training data, for the validation data, and for the test data for which it has gone through no training. Okay, so that is the idea. So first, some pre-processing of data is required. So I need a date time stamp. So I use a new column here. So I put a new column with the date time in this format, and I set that as the index of my data frame. Okay. Previously, the index, you can see, is just a label, is a number 0 to the maximum. So now it is labeled like this. So I've removed the previous date time format from it because I don't need that. So your data frame will look like this now. Okay. Then I need normalization of the data. Normalization can be done in various different ways depending upon the nature of your time series data. So you have to look into what kind of data, time series data that you have. It's a time series data that we have. So there are various ways. One is that you look into the probability distribution of that data. Check for what is the mean value for that data and what is the variance, okay? And then use those two parameters to normalize your data, okay? So you want to have a probability distribution of resulting data so that it is centered at 0, and then it has variations on both sides, positive and negative sides, okay? So this is kind of normalization, that your values are always between -1 and 1, and they're centered at 0. You are doing that kind of normalization. This is one way. Another way is, which I'm using here, is called min-max scaling. So in min-max scaling, you find out the minimum and maximum values of the data, and each value is normalized like this. You subtract the minimum from it, divide it by the difference between min and max. Now this is done by a function from scikit-learn. So I've included scikit-learn, and from that I've importing the pre-processing. So in pre-processing, there is a function, min-max scaler. I call it, and it creates this object scaler, okay? So this object has a function, fit transform. So if I give my database data frame to it, it's going to give me the scale data as a result of it. So D is basically the values obtained after scaling. Now they are not in the form of a data frame now, so I have to put it in the form of data frame. So I will use again, I'll use PD data frame with D and column as DF columns. So it will convert it back to a data frame, a scale data frame. So your values here you can see, for example, if I look at the temperature, -8.2 goes on, -3 it's Germany, so the temperatures are negative or positive. Pressure is 996 here, 1000, something like that. And if you look at the values here, then they are normalized. All the columns are normalized according to their own min-max, okay? So this way you can normalize any time series data that you have. Then I don't want to use all of these 420,000 values. I want to have only the hourly record. So I'm going to do the skipping, okay? So starting with the fifth value at the clock, ticking of the hour on the clock, I then take every sixth value, because every value is taken after 10 minutes, okay? So this will give me values which are from time step 5, 11, so on. So these are hourly values. And then I'm going to get only the temperature values. Temperature, if I plot it, it looks like this, okay? So there are sinusoidal kind of variations. They are not exactly sinusoidal, but there are periodic variations in the temperature, okay? There are some points which are going outside the scale also. These could be some rare events, because it is over a large span, 7 years of time, okay? So anyway, so there are total of 70,000 values in here, about 70,000. So now my data is available, it is scaled, okay? It is normalized, and I can do the splitting. This is where I'm doing the splitting. By the way, in TensorFlow, in Keras, there is a data splitting function available. I'm not using it, but you should try it also. It will automatically split your data according to your needs. You define the percentages, and it will split the data for you, okay? So you can do that also, but this is just an array for me, so I can do the splitting like this. So I've got 60,000 for training, 5,000 for validation, and about 5,100 for testing, okay? But this data is not in the form of I require to train my neural network. Now, what kind of neural network I'm going to use? It will have certain inputs, and then different layers, and then the output, okay? What should be the output? So it's a time series. I should be looking at some values in time, back in time, okay? And based on that, I should be predicting what will be the value in the next hour, okay? So for example, if I choose last 5 hours values, can I predict based on those 5 values the value after the 6th hour? Okay, so that is what my neural network is going to. I'm going to give it certain number of values, and it's going to give me some results. So I need a sequence conversion like this. If I choose this window to be 5, okay, so I give 5 values, I get the 6th value. Then this 6th value will become a part of the next series. The next series will be from x2 to x6, and it should predict x7, and so on, okay? x7 should go there, so the next series starts from, so I'm going hour by hour, okay? So after every hour I want new estimate, new prediction, okay? So these are the predictions, but they become a part of the previous training data. Now this is training data, so I can manipulate my series any way I like because all the values are available to me. Okay, so I rearrange my data like this, okay? For that I've written down this function. I'm not going to go into the details of that, but it works like that. I give the window size. I can change the window size to whatever number I like because there are sufficient number of values available. I'm using 5 values for this particular case. 5, I've seen that it gives me reasonable results. And then I give the window size, and I do this kind of data manipulation. Okay, it's pre-processing still. So the training data, validation, and test data, they are all transformed like this. So I've got X, capital X train, and Y train. So this is a vector. 6,000, well, 5 less than 6,000 times 5. So it's a matrix because every row has got 5 values in it. Every pattern has got 5 values in it. So there are about 6,000 minus 5 patrons in my training data. And these are the corresponding values which I should get as a result of that. Okay, so I'm writing down the shapes of all of these X and Y. You can see the Y values are 6,000 minus 5 here, 5,000 minus 5, and so on. Okay, and now my data is prepared, it's ready. Now I can go with making the neural network. So I include the necessary model and layers and etc. I can include only one Keras and can use it, but then I have to write down everywhere that it is from Keras and that. So I've used this kind of strategy here. I will be using a checkpoint, mean squared error, root mean square, and Adam optimizer. So I'm defining my model as a sequential model. Okay, the input layer has got 5 inputs. Okay, so that is the first layer. Then I've got an LSTM layer with 64 nodes. Each node, you know, is a recurrent neural unit. So there are 64 of them. Then I have a dense layer after that. So this will give me the kind of features. Then on dense layer, I'm going to do the actual training. So I've got 8 neurons with a ReLU as activation function, and final a linear layer just to get the result out. Okay, so this is my network. If I check its summary, it looks like that. Checkpoint, a model checkpoint I'm having because I want to save my model somewhere for reuse. So you can use it to save your model. I'm using save best only model in this case, make that true. And then I compile using mean squared error, Adam optimizer with a initial value of alpha 0.001, and we use the accuracy as the metric. Okay. Then I use fit like any neural network to train this. Here you can see that I've got the training data, and then the validation data is also given along with that. Fit also accepts that, so it makes use of both. So when it is doing training, it is using both data, as you can see here. I'm running it for 50 epochs. My callback function is this. So every time I'm running it, it is keeping a record of whether the model is better than before. So it's going to keep the best model actually out of all of that. So starting with this, you can see there are two. In the first epoch, there are two runs. The first one is for the training data, the second one is for the validation data, and so on. In some of them, only one of them is taken into account, okay, depending upon how it is randomized. And okay, so it's going to do the training 50 epochs. Once it is done, then I'm ready to plot. So from the history that I've gathered, I'm going to plot. I've made a loss function for plotting purposes. So plot loss is my function in which I gave this history, and it's going to plot the data. Okay. So in this, if I plot the history, it's not only going to plot the loss function but validation loss also. So you can see in this case that both the loss and the validation loss, they are following the same trend, which means they are consistent. Okay. I reset this after playing with the numbers. Of course, sometimes you get values which are flat, sometimes they are, but this sounds like reasonable. It's following the same trend as the loss curve is following, the validation is following the same trend, and it's close to it. Okay, even better than that. And then I test the model. Okay, so for that you can use predict. First, I'm going to test it for the training data. Okay, so this is a training test, whether it is giving me the correct results for the training data. Okay, so I get the training predictions. Okay, and make it a part of the data frame which I already have got, and then I can show that the train predictions and the actuals. Okay, they are still normalized. You can see that the values are not the actual temperature values, they're normalized values, but you can compare that they're very close together. Then I can plot them also, some part of it. Okay, so I've plotted a part of this. So you have the actual and test predictions. You can see that, especially in these tricky areas, the trend is being followed, which is interesting. That your network has learned, has got that memory. Okay, it's keeping in view of the previous trends and then making predictions. So it is following that kind of trend. It's close to it. So that was for the training data. For the validation, I do the same. I do the predictions, compare them with the actual values, validation predictions, and they are again very close to the actual values, and then plot them for some other range, and this is the result. Okay, so blue is actual and orange is the test predictions. You can see they are following the trend. This is the actual test where I have got that data for which we haven't done any training. So it is as if that you are going to predict the temperature. If you gather the data for Hamilton or for Toronto, and then do this exercise, you should advise the weatherman that the next few days will be like that. Okay, you can do that with this kind of thing. Okay, so if you do that for that unknown data, you see if the values are quite close, and this is the result, which is amazing. I'm happy with that. It is following. In this case, since this is future prediction, but those predictions are available to me. I haven't done any training for this blue line, and it is predicting it, starting with that initial value. Okay, it is predicting all that result for me, and that was very interesting. And I think you can run a similar kind of problem for local weather or for weather of any city. That gives you a nice, if you have data available, of course, for that city. But for North American cities and European cities, most of the data is available, I think. They are on the grid, and you can have US Geological Survey or Canadian government does that. So all data is available in CVS form for past about 50 years, and so the data is available. Okay, I was looking into how far we have the weather data, and we have quite for majority of the cities, you have to give the coordinates, and it will show you the stations which are closest to that coordinate that you're giving, and you can collect the data from that. for Pearson Airport, from Hamilton Airport, especially the airports, they are on the weather grid. So they have all the devices to measure temperature and all wind velocity and weather conditions, okay? So you can run it for that. Other time series data is not that different from what we have. So if you are talking about stocks, okay, money making, then you can try. I was trying it, I couldn't get, I got hold of some data for, well, for Bitcoin it's very costly, but for other coins which are affordable, you can devise out something like this, okay? And the data is available for past 5 to 10 years, depending upon how old that coin is. So you can have that data from Yahoo Financial, and it's free of cost available to you. Closing and starting data, min and max values for the stocks or for the coin for that day, for past at least 5-6 years it's available. So you can design your neural network based on their data and then can make prediction, help others to make money, or if you want yourself, you should trust your neural network for that, okay? So that is another application. You can go for all other possible time series applications. Like I said, earthquake data, sunspots, scientific data. So how many people come to are using the transit, okay, buses, a special route, a particular route, how many people are using that, and predicting that on that day or in that, even up to day, you can make a good prediction, okay? COVID data, that is publicly available for majority of cities, so you can use that to monitor for you can train it for, well, I don't expect that it'll happen again, but you should get yourself prepared for with that kind of gadget available at your disposal, that you give it some data and it will give you some predictions how the things will move in future. There are other factors involved which I'm not taking into account, okay? Sometimes this is a univariate modeling. There is only one variable in this modeling which I'm using. We have variables affecting each other, okay? So you must take those into account when you are making a better model. So a multivariate model in which you not only have temperature or wind velocity or pressure is an important consideration, okay, because the rain and the wind and the temperature changes accordingly. So cloud cover. So these factors, if you want to make a better system, then that kind of multivariate RNN is required for that, okay? So I'll stop here. I've given some examples of sequence to sequence also. I mean, if in this case we are looking at only one parameter on the output side, but we can make many parameters also, okay? It's just a neural network, and you are going to partition data accordingly, okay? If it is a time series kind of data, you can partition it like that. But you can train a many-to-many kind of mapping with with some modifications in the existing code, okay? All right, so today I was planning something else. I just wanted to cover this part before I move on. So let me move on to the actual part of my today's lecture. This is not the one, it's an old one.